So I'm happy to be here. Thank you to my friends at Kaspersky for giving me the honor to come and speak as part of now my second ICS cert, right? I started the first ICS cert. Now I get to speak with some friends from the other one. This morning I'm going to try to set the stage for why we are here. Why are we concerned in this area of industrial cybersecurity? And what are some of the things that we should do about it? Yeah. So the concept of my talk is going to be think like a hacker, but act like an engineer. I think we need to combine the best attributes of the hacker mindset for how to circumvent security controls, how to break things in order to build things stronger and fix them. And that's where we get the engineer concept from. Today, when I talk about a hacker, maybe it's not the guys with the hoodies and the criminals per se. It's more, I think of the term hacker in the old way. For me, was the 1980s when I was using my old Commodore computer and 300 baud modem, right? So even though we like to wear the hoodie to stay warm, we still have to, I think, keep a positive attitude. And the media and the TV tends to do us a disservice here by criminalizing everybody with a hoodie. So let's do a little bit of a history lesson or overview. In the industrial control system world, you take these black boxes and install them. And quite often you put them in service for maybe up to 30 years. That's a lot different than the computer that sits on your desktop that, every 3-4 years maybe you get a refresh, right? You get a new one. My wife, for example, couldn't wait to get online to order the new iPhone. And I asked her, I said, well, what's wrong with the old one? She said, nothing, but you have to have the new one. Control systems aren't like that, right? We put them in, we design them to last a very long time. The other big challenge, I think, is that originally when we designed these systems, we did not design them to be interconnected to anything else. And over the years, it's almost like an organism, right? It grows by itself and gets all of these network connections to it. And so by osmosis, we've connected all of these systems to everything else. The other, I think, key challenge or difference is, I remember seeing maybe only 1 or 2 weeks ago, Windows, when it was going through an update cycle, Microsoft Windows, it came up with a new message box, and it said, Windows is a service. And so we get into this expectation that operating systems, applications are going to silently just update themselves in the background, and we are only renting the software, right? You're not purchasing it anymore. You're sort of leasing it or renting it. In the control system space, if you need to go and do a firmware update, you might have to take a truck and a crew of many different men and women and update thousands of these devices along a long pipeline or an energy grid, and it could take a long time. It's not as simple as just pushing one button, right? So we have a lot of work ahead of us, I think, right? So if we have all of these systems connected, you would think that we would be doing a good job of separation here, right? Perimeter controls, firewalls, intrusion detection systems, intrusion prevention systems, but that's not the case. My old team in the United States Department of Homeland Security would go out and do a sort of inventory or survey assessment of these facilities, and we found every single year for, I think, the last 5 or 6 years, boundary protection or lack of boundary protection is the #1 challenge in these systems, right? So we interconnect the critical system on the control system side to the enterprise system, and we put not enough defenses in place. There's other key takeaways I think that you can get from these kinds of analysis, but overall, it's this interconnectivity, right? And we're not paying attention to all of those little touch points. So let's look at some of those, and I'll admit that I stole this slide from my friend Eric Byers, who is a good Canadian brother with me, I guess. So Eric and I have been doing this for a long time. The other thing I would hear from the field teams when we went out is that, oh, we have an air gap, right? We're completely isolated from the control system to the rest of the world. And I will tell you that almost every single time, these air gaps are not true. It's a false, right? So you need to think about, well, how do you get changes into the system or get data out of the system? Do you use removable media, USB stick, CD-ROM drive? Do you have a vendor that comes with their laptop and plugs their laptop into your machine to do some programming, and then takes that same laptop and plugs it into, the neighbor's machine in the next city? How many machines have they plugged this into, right? I used to make a joke that it's like sharing your toothbrush. You just don't want to do it, right? Do not let the vendor come and plug their computer into your system. If you're doing vendor maintenance, you should be supplying the computer to the vendor, having them put their software on it and be in compliance with your security controls and your security procedures. And in some cases, if your security requirements are high enough, you should also be making them leave that computer on your facility, right? They should not be able to take it off-site with them. They should have to keep it. You should keep it, I mean. Actually, one of the good things I've seen is when we start adding wireless into these systems, we actually tend to pay more attention to security. I think as humans, we think, oh, wireless must be insecure. So we tend to do, I think, a little bit better job when we're using industrial wireless protocols. So now that we have these systems all interconnected with each other, what is the problem, right? And I think a lot of people get hung up on the fact that, oh, my system is connected, but that's okay. You have to be a nation-state level APT type of capability to be able to get into these systems. Well, no. These systems can suffer from all of the same malware and bugs that any contemporary enterprise system can, right? These systems have commercial off-the-shelf operating systems that can, we still see systems that, for example, are susceptible to some of the old, MS-08 and 06. Those are old CVE numbers, right? These are not new issues. We talk about supply chain issues. If you have a PLC that has a communications circuit or chip in it, and that chipset has a vulnerability in it, whose job is it to make sure that you, as the end user that is maintaining that PLC, knows now that that chipset has a vulnerability in it, right? And how do you even know as a user? So you call your vendor and you say, hey, am I susceptible to this? And in many cases, they don't know. It's only their developers that knew what chips they used inside, right? And so this was a good example of SSL challenges in Heartbleed, right? Where we had embedded code that we didn't understand where it was running. So the point is that these systems can get sick, I guess, from a lot of the malware that isn't necessarily targeted, right? We are vulnerable to all of the different malware, right? Not just the targeted stuff. So Kaspersky did a survey here in the past year to ask people what were their concerns with regards to the security and safety of these industrial control systems. And I picked out two of the top concerns. And I think Eugene Kaspersky, in his message to us this morning, mentioned this, that it's not just about the security of these control systems, right? This is a national security or safety issue. So when you look at the safety issues, the big consistent messages that come out is that we're concerned about either damage to the physical equipment, some of this equipment costs many, many millions of dollars, or we're talking about injury to our workers, right? Safety issues. And when you start to see some of the safety instrumented system environments getting breached with Triton, Trisis, Hatman, whatever you want to call it, this is now, I think, probably the biggest concern we have in industry. No longer are we talking about just disruption to the process. Now we are talking about actual damage to the people, right? Injury to the people. So we kind of have this confluence, I think, of two key challenging areas, right? We have this overlap of safety and security. And as engineers, we know how to address safety, we know how to address security, and we can learn from each other, I think, in how to do this effectively. The challenges that we seem to have is, that we have forgotten how to use some of these basic engineering principles, I think. And so we get so concentrated or so focused on the cybersecurity challenge that we forget, oh yeah, we went to school and they showed us how to, do a safety analysis of a system, and you should do these things before you put the system in place, right? The other thing, and I could be guilty of this in some cases, I think, is we have not given enough risk assessment or prioritization to the system. We have 1,000 PLCs in our environment. All of them need to be patched. Well, maybe you need to take a more careful look at that and do a risk analysis and prioritize which problems you fix first, right? You can't fix everything all at the same time. Okay, so now I'm going to shift a little bit into a concept that Idaho National Laboratory, who I have worked with for many years, calls consequence-driven informed engineering, right? Cyber-informed engineering. And what they're talking about is let's use the information, let's use the knowledge that we have gained from these cyber types of events, and when we're building new systems, engineer that in, right? And do it through a very methodical process. Now, you cannot do this with just one person or one team. This is not just cybersecurity engineers, right? You need to kind of put the red team hat on. You need to think like somebody trying to break into the system. Or you need to think like somebody trying to cause damage to your system, right? So think like an adversary. Then you also have to go through and analyze very methodically all of these systems and all of their interconnections. So you have to think like a systems analyst. You also have to think like a hacker, how do you break these systems, right? Where are the weaknesses in each one of these systems, and how can I exploit that? And if I can exploit it, what can I then do? Now, you look like the engineer, and you come back and you put all of that together, and you build the best system you can with all of that information and all of those methods, right? So first steps, right? You need to go through and think like what we would say, think like the adversary. So if I am a competitor and I'm trying to cause damage to your facility, or if I am an environmental group that doesn't like the fact that you're, doing something to the land, how am I going to cause the most damage? Well, in the safety area, we have ways of ranking those damages, right? And we have ways of mitigating. So you put layers of protection into place. And at every single step, whether that's the basic process control system, or whether that's the safety instrumented system, or whether that's a mechanical relief system, or a dam, a containment wall around a tank, we put these kinds of barriers into place. So you have to think about how am I trying to disrupt these systems, right? After you have done that, now you have to go and do a complete inventory of every system that can affect that process, So what is the dangerous process or the critical process you're trying to save? Now go and look methodically at every single system. And some of these aren't easy, because I think asset inventory is one of the big challenges we have, in the control systems environment. People just do not know what is on their networks. There's stuff in closets and underneath cabinets, and it's very difficult to get a good asset inventory. Luckily, we see some good technology coming along there. Once you've gone and found all of the systems, now you can start to apply what I would say would be, this is where you are thinking like the hacker, right? You're thinking about, how do I break these systems? My good friends at SANS, Mike Asante and Robert Lee, adapted a piece of work that was the Lockheed Martin cyber kill chain. And essentially what it was is they went through each and every step of an attack and mapped out what are all the different things that enable the attacks to occur, and then how do you take those things away from the attacker. And every time you go through that, you have an opportunity to disrupt what the attacker is doing, right? So the first part of it is to gain access to the system. And most of the time, this is where the malware does not have to have any kind of control systems knowledge. This is social engineering, this is spear phishing, this is water holing, this is just getting access to the facility or to the target that you're looking for. Once you are inside that facility, or you have access to the engineers, now you want to go through and look at the specific control system parts that you want to target in the attack. And once again, you can go through a very specific or precise methodology to take away the opportunity for the attack to succeed. And every time you can put a barrier in place and make it harder for the attack to succeed, that is a win for the defender, right? So once you've done all of that, you've gone and prioritized your systems. You know which systems are important to you. You've gone and found all of your assets, so you know where every piece of equipment is, every system, every network, and you've put all the protections in place. You've purchased the best technology, and you have the best people doing this work. You're still not done. This is where I get a little bit controversial, I think, which is good. Some of these systems are so important, I will tell you, I don't think they should be cyber. What do I mean by that? I mean that we have gone to the point now of putting everything into these programmable devices. So I can buy one device, but I can reprogram it to do anything in my facility. I think we need to go and design specific non-tamperable, tamper-proof circuits to do certain shutdown functions, right? So we've been misquoted, or people misunderstand and sometimes think we're trying to tell them to go back to the old mechanical relays for logic. And that, I don't think that's the case, right? But what we are talking about is if you have a circuit that a shutdown function that needs to read certain sensors and needs to then drive certain valves, maybe we shouldn't put that in a safety instrumented system. Maybe if that function is so important that the whole plant will be destroyed, or it will kill many people if that function fails, maybe we should spend some extra money and engineer it in a discrete components with gates, FPGA, something that is burned in at manufacturing, and you cannot change. If you need to change the logic, you need to go build it again, and it might cost you some money, right? But if it saves people's lives, or if it saves these millions of dollars machines, then I think that may be considered a worthwhile investment. So, kind of refresh here, the 4 steps that you need to go through when you're looking at these systems is find out what is important to me. What is the most important business function? what makes all of the money for the facility, and then prioritize those functions, right? And start with only the most highest of consequence first. Don't try to do everything at once. Second, go through and look at every single system, every network, every switch, every PLC, every sensor that has smart networks and things around it, every valve and motor that has some sort of intelligence to it, and inventory it, and understand what role does this piece of equipment have in supporting that key business function. Third, put on your pen test red team hat. Try to break it. How do I break or break into or find vulnerabilities in all of those systems? And then go and apply technology or procedural controls to take all of those weaknesses or vulnerabilities off the table. And last, if you can't take all the vulnerability off the table, if all the risk cannot be taken away, now you need to consider doing something in a non-cyber, non-programmable way. What are the mechanical protections around this system? Some of these controls could be procedural based, right? You could have a policy that said, when we get into this dangerous part of how this plant works, we're going to intentionally, put our systems into this kind of state to make it safer. Anyway, so that is my, plea to you is go through these systems methodically, understand how they work, understand where they can be broken, and then in some cases, take them away. Do the controls some other way. So in the respect of everybody's time, I will hand my microphone back to our MC, and maybe he will do some dancing for you if there's good music. So, I will be here for the next 2 days, so if you want to ask me any questions, feel free to come up with in the hallway or over a beer or something later on, and we can answer all your questions. So thank you very much.
Thanks, Marty.